9 was integral on your calculator, and we did at least one of those. So I skipped over these, so let's go back. Basically, we've been doing area under a curve with rectangles. So this would, and there's a function here, look at the table version. Estimating area under a curve with rectangles. Well, sometimes we can find the exact area under the curve geometrically, basically based on shapes. So if we know a certain shape that a line or a curve represents, we can actually find the exact area. So this 100% boils down to just a geometric shape that we're doing. So
The rectangle.
yes, that is one. So so here we go. Find the following areas. Think geometrically. So the first one is what this says. Find the area under the curve from 1/2 to 3/2, 0.5 to 1.5, of -2x plus 4. So most of these I'm going to make a sketch. You also are allowed to use your graphing calculator, so you can put it in if you weren't sure. We know this is a line with a y-intercept of 4. A line with a y-intercept of 4, and a slope of -2, so that's down 2, right 1, and down 2, right 1. Right, I could keep going, but, I keep going, but I'm already at 2, and we're going from 0.5, which would be here, to 1.5, which would be there. Right, from 1/2 to 3/2. So let me draw in what the area of the curve is. I'm just going to put a line down at, there's 0.5, and then line down at 1.5, and I'll shade that in, and that's what we're finding, the area of that. So there's a line, area under that line from 0.5, 1.5. And what shape do we get? Trapezoid. And if you forget the trapezoid formula, you can also, trapezoids always break down into triangle and rectangle. So like if you wanted, you could just draw a line there and do the area of that triangle and an area of a rectangle. All right, and just add them up. I'm going to do a trapezoid though. All right, so this is going to be the area of the trapezoid. Trapezoid is 1/2 height, base 1 plus base 2. Alright, so this will be 1/2. Now remember, the height is the non-parallel sides. So the parallel sides are here and here. So this is the height right there. Remember, we just did the trapezoid rule.
Yeah.
And the height was actually the bottom part. So that height will be 0.5 to 1.5, which is a length of 1. Okay, and then here I just got to do base 1 plus base 2, so that's the parallel sides in green here. Those are just the y values at 0.5 and the y value at 1.5. So really, remember we're doing f of 3 and those like that, back with rectangles and such. That's what I'm really doing. So right here is going to be f, I'll put it maybe above, f of 0.5 and f of 1.5. Just getting the heights, the y values. So let's put in 0.5 to that function. I put in 0.5, and you can also look at your table. You can enter this in your calculator. -2 times 0.5, that's going to be -1. -1 plus 4, we get 3. I'll put in 1.5, so I got -2 times 1.5 plus 4. So let's see, this will be -3 plus 4, so 1. Okay, so it's going to be 1/2 times 1, which is 1/2, 3 plus 1, which is 4, and so we get 2. So again, just makes a shape, and we just fully go with what the shape is, to the area of that shape. Again, if you wanted, you could have broken it down into a triangle and a rectangle. that's what each is going to be. I'm going to give you some more examples, different shapes up here. Lots on one? So let's go to 2. Here's the function from -2 to 2. Anybody, now you, again, you can put this in your calculator, but anybody know what that's going to be?
Is that just like,
No, close. What? No. Well, if we put it in the full, so if I set that equal to y, I set that equal to y and squared both sides, and then added x squared, I'd get this. You recognize that back from geometry? X squared plus y squared equals 4. Square rule. I'm just looking for the shape. Circle, nice. Okay, yeah, it's a circle. So this, you'd think it'd be a circle, but the problem with circles, they're not functions.
semicircle.
So it ends up being just a semicircle, yeah. And again, if you put this in your calculator, which, I mean, we could, I guess I'll open that up. But it's just going to show you the top part of a semicircle. Here, I guess I'll, might as well now. Square root of okay, so right there, and that's fine. So notice the circle, it's a semicircle, goes from -2 to 2, and it goes up to a y value of 2. All right, so I'm gonna make a little sketch of that. Now, it does say we're going from -2 to 2, right? We're finding that whole area. It could just easily been to like -2 to 0. So then you'd only do half of that semicircle. Okay, but it does say that we're doing the entire area under that curve, and so it's just a semicircle. By the way, so this was trap. This one's semicircle. So what's the area formula?
Half.
Isn't it like pi r squared and then you divide by 2?
Mm-hmm. Pi r squared divided by 2, or you could half pi r squared. Because you want half the circle, either one. I'm gonna do this. That's all right. Just don't want to do like all divided by 2, but you could. Okay, nice. So then all we need is the radius. The radius just from 0 to 2, or if you're going vertically up, it's 2. Go. So that's 4. 2 squared is 4. And half of, that would be 4 pi is 2 pi. You can, back from geometry, you can leave your answer in terms of pi. If you'd like to put it as a decimal, you can as well. So it's good to recognize that as a semicircle, but we're in graphing calculator, okay, because you're allowed to use that, and that can help you remember. Okay, one more. Any thoughts on 2? Can we move on to 3? Okay, so this one, -1 to 1 is the interval of 1 minus absolute value of x. And we can use our graphing calculator, but let's just do it up here. So 1 is plus 1, takes us up 1. And then this is a v, right, absolute value. But the negative turns it upside down. So it's actually this, but then we're moved up 1. So we're starting at 1 here. It's going to be this v. Zero. So we are going, again, got to pay attention to this, -1 to 1. And again, if you looked at your graph, or if we just plug in the x value of 1, we'd get 0. It'd be 1 minus 1, 0. So it confirms that x coordinate is 1. And that's -1. And so we want from -1 to 1, which is that. So basically you could think of it as one big triangle. I also see 2 little triangles. Either way you want to think about it, but basically number 3 is a some sort of triangle. So I think I'm just going to do this big triangle here. 1/2 base times height. The base then is 2, and the height is 1. And so we get 1. Now something we'll see in the practice that I didn't have up here, and we'll continue to see overall, is what if I had said, area under the curve from, let's say, 0 to 2. Okay, so now green. It would actually be, so here's 2. It would actually have part below the x, right? If it's below the x-axis, you go up to the curve, to the x-axis. Sorry. So it's not below the curve, it's actually above the curve. So if I said 0 to 2, it would have been this. So then what would have the area been?
2.
1/2 base times height, multiplied by 2.
Look at that. Yes. Uh-uh.
2.
Nope.
One.
0. Because when it goes below the x-axis, it's negative. So this would have been an area of 1/2. This would have been an area of negative 1/2. And so together it would be 0. All right, so this is just a review. Anything below the x-axis is negative area. That was.
Oh, so you combine the 2?
I went too far. That was this. Yeah. So again, our problem, it was 1, but if it was from 0 to 2, it would have been a positive half triangle, a negative because it's below, and adding those would have been 0. So my point there is below the x-axis, 0. Is negative, I'm sorry. All right, I had one more example, but I'm going to skip that for time and go on to the second part, integration rules. Any thoughts on this one? So break it down into shapes that we know. I do want to say one thing at the bottom. What we're starting to figure out and piece together is, from the beginning we said an integral is an antiderivative, but the second way is area under the curve. And again, very, very soon, we're going to have a theorem that kind of combines those. So it's either finding an antiderivative or finding the area under the curve. Soon it's going to be both. Okay, so last thing we're going to do today is integration rules. These are fun. I really like these.
So fun.
They are. This is probably my favorite part of this unit. It's like a little puzzle equation you're trying to solve. So this is all area under a curve, but it's things that we can do to simplify the expression and help us solve for different areas. So it's kind of like properties of integrals, just like we have properties of limits or derivatives. Okay, so here's the first one. The 0 property for integrals. This says if you're integrating from a to a, the area under the curve is 0. So if here's my function, and I want to integrate at a point, there's no area under the curve. It's just a point. I draw a line to represent it, but there's actually nothing underneath an exact point, because a point is infinitely small. We represent it by a dot. But there's nothing under there. So if you have an integral of the same number, 3 to 3, then it's going to be 0. That one. Right, nothing under there if you're going from the same number. The next one is the order property. This one says if you switch the order of the integral, you can make it negative. So how about, actually, all right, so if I'm going from, let's just say 1 to 3 of some curve, that's like this. I'm just showing an example just to make it up and look like that. Well, I can also integrate in reverse. So 3 to 1, I can flip those. You see it was b to a and then a to b. I can flip those and it's the negative value. And I think one way I'm going to try and represent it is this. Basically, basically we read left to right. Okay, basically we, oh, darn it, this is not working. All right, well, let's see if I basically, let's see if I can flip this one. All right, I'm going 1 to 3 now. I'm going to go 3 to 1. Okay. So we read left to right. So 1 to 3 would be that area, be a positive number. But now if I go 3 to 1, think about if I would go left to right. It actually would be in the reverse direction. And I can think of it, you can just turn your paper upside down. Think of it like that. 3 to 1, now it's the same amount of area, but it'd be below the x-axis. So that's negative. So I'm just trying to show you that if you reverse the order, you will have the same area, the same amount, but it will be negative, just going the reverse direction. Okay, that is the order property for integrals. This next one I think is the funnest and maybe the most important one. Additivity. Additivity property. This one is going to make sense too. Okay, here's A, B, and C. It just says if I have the area under the curve from A to B, right there, plus the area of the curve from B to C, wouldn't that equal the area of the curve from A to C?
Yeah.
That's all it says. This part plus this part. It's the same as segment addition, if you remember from geometry. So it's this area plus this area equals the whole area. That's what it says. It's kind of like adding areas under a curve. Part 1 plus part 2 equals the whole. The next two are just very similar to limits, derivatives. It's the same kind of thing. Constant multiple rule. So you remember for derivatives and limits, it was like, oh, if you're doing the derivative of 3 times e to the x, or 3 times something, you can just pull the 3 out. Right? A constant has no effect on the derivative or the limit. So same thing here with an integral. You can pull that c out. Right? So if you have a number in front, a coefficient, you can pull it out.
Are we ever gonna do like stuff with limits again, or are they just
Open up.
long gone?
First of all, yeah, a little bit, and if you go into higher calc classes, then yes, you will. I mainly think of this. We kind of do calc 1 and 2, so calc 3. There's definitely some stuff in there. Not a ton, but some. Sum and difference. Same with okay, derivative. I'm saying derivative. I'm writing integral. Derivative of this, or limit, finding the limit of some value of this. Right, you could do them separately. Each one. This is the same thing with integrals. If you have an integral of a sum, you could do each one separately. So you could evaluate this and then evaluate that one. Same thing if it was minus. So this is very, very similar to limits and derivatives. All right, and finally, this one gives you the constant rule gives you a kind of formula if you're just doing the integral, the area under the curve of a number. So if it's like the integral of -1 to 2 of the function 3. So 3 being the horizontal line y equals 3. Okay. And what this says is if you're doing a number, I always think about it geometrically because it becomes a rectangle. And that's -1 and 2. It just becomes a rectangle I'm finding. But this gives you a formula that also works. What it does is it just says, well, here's the height of your rectangle. It's the number, like here, my example 3. And then b minus a gives you the width of the rectangle here. So 2 minus -1 would be 3 as well. It's just kind of a formula. You never actually have to know that one because you can always make a picture, like I do. Okay, so let's try some examples with that to finish up. So any thoughts on those properties right now? So here's the good stuff. Where they give you some values we know. So we don't know the exact function here. I'm just going to say f of x or h of x. That one says h. Notice that. But we do know certain areas under the curve for the function. So for the function f, the area under the curve from -1 to 1 is 5. Another one for f, here's another one for f, and here's one for h. And with this knowledge, we can actually figure out some other values. Okay. We do have to know that they're continuous functions, and we can find the integral if possible. So sometimes you might be able to say it's not possible. All right, so let's try it out. First one, the integral from 4 to 1 of f of x. Well, I don't see a 4 to 1 up here, but actually no, I don't like that order. Do you?
Now let's flip
No,
it.
let's flip it. and
Oh.
everything.
That's it. There we go. So let's flip it. I don't like it because traditionally you want the lower value on bottom, and this one's just reversed. So flip it. Now this one we do know, right here, right? The area of the curve of 1 to 4 for f of x is -2. And so this one becomes, now don't forget we had a negative, so it becomes, that negative comes down, and then this is -2. Negative negative becomes positive 2.
Let's go.
Isn't that fun? Little properties, you know?
No, I'm digging it right now.
I like that. Okay. So that one was using the order property, number 2 up above, where we just flipped it. Next one, -1 to 4 for f of x. So we'll get to an h of x1 in a second, but we don't, not yet. You might say there is no -1 to 4.
So then we gotta make it.
We gotta make something that would be -1 to 4. So really, I mean, what we're thinking of right now is we have a curve. So we want to find the entire area -1 to 4, but we don't have it. So do you know what property we're using?
Sums.
No.
Additivity.
Not
Yeah.
number 5, number 3, additivity.
Additivity.
So the additivity says you can break it up a total into the sum of its parts. So for example, -1 to 1, we do know. We do have -1 to 1, it's 5. I'll write it out in expression here. But I'm writing it graphically right now. We do have -1 to 1, right? It's 5.
Yep. And then 1 to 4.
And then 1 to 4. So my drawing actually isn't to scale. It's going down here actually. And it would be the sum of this and this. It'd be an area under, below the x-axis to the curve. So my drawing is not to scale, but let's just say that it was. So we do have 1 to 4, and it's -2. So basically we used additivity. We just broke this up. We used number 3 from above, additivity. And just said this would be equivalent to the area of -1 to 1 of f of x plus the area of the curve from 1 to 4. Because we have each of those. And so it's 5 for that one, and then -2 for this one, which is 3.
Let's go. Wow. You would know.
So good on those 2? Order and then additivity. Let's see what I can finish up. I can finish 2 more. Yeah.
If we don't write like the second step there out.
This you don't
just
have
the
to do
numbers,
that.
then-
Yeah, you can just have the numbers. The next one has an h in it. Now, what we should see here is there's a 2 in front.
Constant.
So we're using number 4, the constant rule there. And 3 here as well. We're going to pull that 3 out. Because there's a plus, we're also using the sum and difference rule. The sum rule. Which says we can do each one separately. So basically, I'm going to break this up into this. I can pull the 2 out and do the area under the curve from -1 to 1 of f of x. I can get that. Then plus, I can pull the 3 out of this one and do -1 to 1 of h of x. And then I have each of those values. So -1 to 1 of f was the 5, plus 3, and then -1 to 1 of h is 7. So 10 plus 21, 31.
Is that to the -1?
No, that's the integral from the last one. That's the integral from the last one.
Yeah.
Okay, let's try and do one more. Number 4, we'll finish up 5. 0 to 1 of f of x. So there is no 0 to 1. There's actually no 0 up here. Lots of times students want to look at this one. Right? That's negative 1 to 1. So lots of times students want to say it's 2.5 for this. They want to say, oh, well, we know it's half of negative 1 to 1.
Can't assume anything.
Can't assume, exactly. We don't know if it's symmetrical, if this function was symmetrical from negative 1 to 1. Yeah, we could just cut it in half. But we don't know for sure. So, and there's no additivity, there's no 0 up here for a lower or upper limit of integration. So you can put no solution, I'm going to put cannot be determined. Let's stop there. Okay, to finish number 5 up. This is the area under the curve from 1 to 2 of f of x. Doesn't look like we fully have this one, but what we can do is we can write a different integral that would be equivalent to 1 to 2. So make sure, yeah, there we go. So here's what I can do. I can do 1 to 2 of f of x plus 1 to 4 of f, plus 2 to 4 of f of x, excuse me, equals the integral of 1 to 4 of f of x. So this is actually using additivity, and it's the same as number 2. However, instead of asking for the total, this one has one of the parts given, that one. They're asking for the total, which would be that number here. So I'm just going to call this one x. This is what we're looking for. And then 2 to 4 of f of x is 1. That's the one we'll write over here. Equals, and then the integral from 1 to 4 of f of x is negative 2. And so then we can just do a little solve, subtract 1, and we get negative